All right, so in this first sort of extra video, I want to show you why it's important to have these y's match up here. And actually, specifically, not necessarily even looking at functions, although I'll show you my example with functions. I want to show you why this assumption here is needed to get these domains to match up. So in order to connect things a little bit more easily with what's going on here, I'm going to use f and g in my notation rather than s and t. So let me rewrite this with f and g rather than s and t. So here's my question. So first observation, theorem 62.1, just rewritten with f's and g's rather than s's and t's, says that if the range of f is a subset of the domain of g, then the domain of g composed with f is the same as the domain of f. So my question then is, do we really need this hypothesis? Do we really need range f subset domain g for this to work? So let me try to construct an example just in pictures where this is violated. And let's see if we can rig the example. So I mean, it could be that this is violated and sometimes you still get this equality since it's a one-way implication. But let me see if I can get this to be violated and have this not be equal. Then I'll see that the assumption is actually needed. So I'm going to define three sets, x, y, and z, and I'm not really going to define them. I'm just going to stick with pictures. So there's a bunch of dots here, some dots here, some dots here. It doesn't really matter how many, and I'm not going to label the dots. Just pretend they are distinct elements. Then here I'm going to draw f and g. There will be some connections of arrows, and then g composed with f will be what we get when we mush the pictures together. So in the end, let me make this room here. In the end, okay, here's our backwards notation. I've got to flip these around before I stick the composition symbol between them. So in the end, I'm going to get a picture here where I connect the edges that go from beginning to end. And I want to see if I can violate this. So first I'm going to try to violate this. So the range of f, I want to make it so that the range of f is not a subset of the domain of g. So that means I want there to be things that are in the range of f, but not in the domain of g. So what's the range of f? It's all of those things that, all of these dots that have a friend on the left side, right? So that's the range of f. So let me arrange it so that, I don't know, let's say the first three dots are in the range of f. So let me do this, 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 maybe that. So now the range of f is these, consists of these dots, right? And now I'm going to make sure that that's not a subset of the domain of g. So the domain of g is the collection of dots that have a friend on the right side. And I don't have to make these functions, by the way, for this discussion to make sense, but I'm going to just to try to more closely match the context down here. Okay, so let me make the domain of g not contain the range of f as a subset. So I'll just make it exclude something. How about I make it exclude this one? So let me do this for the domain of g. I'll even make it include this randomly for no reason. So it includes this. I'll exclude this one. And it can include this one, maybe. So there's g. So now it's definitely true that the range of f is not a subset of the domain of g, right? Because here's something that's in the range of f, but not in the domain of g. Now let me draw the composite. So let me just figure out what all the paths are. So I see a path here from the first one here to the first one there, with this as the middleman. So there we are, first to first. And then let's see, down here I see a path from the second dot over to the second dot. So that one has this as the middleman. and then I see a path from the third dot. Nope, nothing goes from the third dot. See? Any path you try to take from the third dot ends in y and has nowhere left to go. Okay, but there's one from the last dot over to the middle dot here. So I have this. All right, now let's compare domains. Do we have the domain of the composite equals the domain of f? What's the domain of f? It consists of this, and this, and this, and this, right? What's the domain of the composite? It consists of this, and this, and this. Ah, the domain shrank. So you see, when you compose functions, the domain can shrink if the range of the first function that's being applied in the composite is not fully contained in the domain of the second one. Now, here's a situation. What this is showing you, Theorem 63 Part 2, is showing you a situation where the domain does not shrink. It's showing you, look, the domain of f was x. After composing it, after saying after f do g, the domain is still x. So the domain does not shrink. Now, it's tempting from this picture to say, like, look, f has green edges from the x blob to the y blob, and g has them from the y blob to the z blob. So what gives? Isn't this saying that g composed with f should go from the x blob to the z blob? Do you see the possible dissonance between the picture here and the result here? This is saying g composed with f should map the x blob to the z blob. Well, hang on. Just because I'm drawing a picture where I have a bunch of green arrows going from y to z, that doesn't mean g maps y to z, right? What's actually the domain of g here? The domain of g consists of this, and this, and this, right? So I would not say g maps y to z. That's the problem. We don't have g maps y to z. We have f maps x to y, but we don't have g maps y to z. We have g maps some smaller subset of y to z. That's the problem. So that's why this wouldn't apply in this situation. And when this does apply, when you really have f maps x to y and g maps y to z, that's the exact situation where the domain doesn't shrink after you compose. So there's no law against composing functions where the composition leads to domain shrinkage. That's fine, right? Like, this is allowing for it. It's totally fine, and you can just do it. But you can see that working with composites is a lot friendlier when the domain doesn't shrink. So we try to arrange things so that the functions that you're composing have this kind of these matching parts. The codomain of the first function, which is confusingly written on the right, equals the domain of the second function, which is confusingly written on the left.